Meine Damen und Herren, ich möchte Sie ganz herzlich auf Deutsch vorläufig noch begrüßen zu dieser neuen Serie von Einstein Lectures, die sich offenbar langsam traditionalisieren. Und ich begrüße Sie ganz herzlich im Namen der Universität Bern und der Albert Einstein Gesellschaft, die zusammen diese Events organisieren. Und ich lade jetzt Herrn Wiese ein, den Referenten von heute, morgen und übermorgen auf Englisch einzuführen.
Yeah, welcome everybody. I'd like to welcome you all on behalf of the Faculty of Science and the Albert Einstein Center for Fundamental Physics to our seventh series of Einstein lectures. And it is my tremendous pleasure to introduce to you Professor Alan Guth from MIT, the Massachusetts Institute of Technology in Cambridge near Boston. Alan Guth was born in New Brunswick in the state of New Jersey, and he studied physics at MIT and got his PhD degree there in the year 1972. Now, after that, he pursued a postdoc career at Princeton University, at Cornell, also at the Stanford Linear Accelerator Center, that's SLAC. And so he had actually altogether 4 postdoc positions. And as he describes in his book, his career was actually progressing at a rather slow pace until in 1979, he got the idea of the inflationary universe, which caught a tremendous amount of attention. And actually, just a few weeks or so after giving a seminar at SLAC where he introduced the idea to the public, he got a lot of job offers, and he accepted a job offer from MIT. He returned to MIT in 1980 as an associate professor, and now he is holding the Victor Weisskopf Chair at MIT and is working there already for quite a while. He also got a lot of important prizes for his discovery. He won the Dirac Medal, he won the Fundamental Physics Prize, and most recently he won the Kavli Prize of the year 2014. He is also well known for a great communicator of science. I would also like to mention that he has written a book for the general public entitled The Inflationary Universe, and it's actually quite interesting. The book is not only explaining the idea of the inflationary universe, it also explains how he conceived the idea and how the idea was developed further in the scientific community. So it also gives you a good idea how research is actually working in a modern environment. Now, concerning the idea itself, all I want to say is that according to standard Big Bang theory, the universe was created in a Big Bang 13.8 billion years ago, and this idea of the inflationary universe concerns really the very tiny fraction of the very first second after the Big Bang, where according to Alan Guth, the universe has gone a tremendous expansion, much, much faster than the expansion of the universe that is still going on today. And so that is what forms the basis of his lectures. Today he will connect the idea of the inflationary universe with the idea of a multiverse. Tomorrow he will lecture at 5:15, also in this room, and he will talk about eternal inflation. And finally, on Wednesday, again at the same time as today, at 7:30, he will consider the universe in relation to the direction of time, to the arrow of time. So I think we are all very excited to learn about these things, and so without further ado, I give the word to Alan Guth.
Thank you very much, Uwe. Let me say first of all that This is my first trip to Bern in 10 years, I think, and it's a wonderful place, and I'm very happy to be here, and I really want to thank the organizers for making everything so smooth and lovely. And I'd like to thank you all for coming. It's a wonderful crowd here tonight, and I find that very, very pleasing. In tonight's talk, I would like to basically talk about three things. For the first third or so of my talk, I will try to describe for you how inflation works. And for the second third, I will talk about what the evidence is that our universe actually underwent this process called inflation. And then the third part will be what's reflected in the latter part of the title, the idea of a multiverse. And I'd like to describe how inflation does not necessarily imply that we live in a multiverse, but at least suggests that it's a good possibility that we live not in just an isolated universe, but a universe that's part of a collection of universes, which we call a multiverse. So that's the agenda. So let me begin kind of at the beginning. Let's see if this works. It's not working. Oh, not working for a good reason. You see, I'm not as smart as Uwe said. Let's see if it works now. Yes. OK. I'm going to begin by talking about the conventional Big Bang just to set the stage, one slide worth of conventional Big Bang theory. The conventional Big Bang theory is the theory that the universe as we know it began some 13 to 15 billion years ago, or more precisely 13.82 plus or minus 0.05 billion years ago. The initial state was a hot, dense, uniform soup of particles that filled space uniformly in the context of this conventional Big Bang theory and was expanding extremely rapidly. The theory describes how the early universe expanded and cooled. It describes how the light chemical elements were formed. The point here is that the conventional Big Bang theory begins at a point where the universe was so hot that even the nuclei of atoms would not have been stable. So the nuclei that exist in the universe today have to actually be formed in the Big Bang or later. And we now think that most of the elements around us were formed later in the interior of stars, which explode and spew these heavier elements out into space, ready to recollect in later generation stars like our own sun. But the latest chemical elements we still think were produced primarily in the Big Bang explosion itself. And we could use what we know about nuclear physics and what we know about cosmology to actually calculate the expected abundances of these light nuclei. And it's a big success. And it's a process which we think started about 1 second after the beginning. So it really traces the universe back to very early times and shows that apparently physics as we know it can correctly describe the universe at those very early times. Inflation goes back even earlier still, as we'll see. The theory also describes how the matter clumps and forms stars and galaxies and so on. That's still to some extent a work in progress, but it certainly seems to be successful. We think we can understand how structures in the universe form in terms of conditions immediately after the Big Bang. What I guess I want to focus on really is what the conventional Big Bang theory does not describe, because that is where inflation comes in. It turns out that the conventional Big Bang theory does not describe anything about what caused the expansion itself, in spite of the fact that somehow this theory came to be called the Big Bang theory. What it really says nothing whatever about is the Big Bang itself. It really only describes the aftermath of a bang. I like to say that it says nothing about what banged, why it banged, or what happened before it banged. So it really is a bangless theory. In addition, the conventional Big Bang theory says nothing about where the matter in the universe came from. In the conventional Big Bang theory, for every particle that exists in the universe today, there was at least a precursor particle that existed from the very beginning of the description. It turns out that inflation actually does offer possible answers to these questions, which I think makes it very exciting. So let's get on to talk about inflation. Inflation is a theory really about the bang of the Big Bang. That is, inflation is a theory of what propelled the gigantic expansion that we're still seeing in the universe today. And before the possibility of inflation was known, Big Bang theorists really did not even attempt to describe what caused the expansion. Inflation explains this expansion in terms of gravitational repulsion, which I think may come to as a surprise to many of you. It certainly came as a surprise to me and many of my colleagues when these ideas were young. It turns out that since the advent of general relativity, gravity has been in principle known to be able to behave either attractively or repulsively. Newtonian gravity, of course, is purely attractive. So this would not have been at all possible in the context of purely Newtonian gravity. But general relativity offers the possibility of gravitational repulsion. And I like to consider this a kind of a miracle of physics. And I will advertise inflation as being essentially the consequence of two miracles of physics. Now, physicists aren't supposed to believe in miracles, I'm told. So I should explain what I mean by a miracle of physics. It's basically a fact about the laws of physics themselves, which have two properties. One, it was never taught to me when I was a student. And two, these are properties that are so far-reaching that they really can change our picture of the universe as a whole. And inflation, as I said, is essentially the consequence of two of these miracles of physics, the first of which is this idea of gravitational repulsion. As I mentioned, gravitational repulsion has really been part of our system of describing things since the advent of general relativity. So it really is a product of our friend Einstein, who we are celebrating in these lectures. Einstein, in fact, used the possibility of gravitational repulsion very early in his original model of cosmology. Einstein was convinced, like almost everybody at his time and earlier, that the universe was static. There was not yet any evidence for expansion, and nobody really anticipated the expansion of the universe. But when Einstein built his theory of general relativity and tried to describe the universe using general relativity, he discovered what is almost obvious, that gravity is attractive by and large, and his initial formulation contained only the attractive aspects of gravity. And that meant that you could not have a static universe. The universe would collapse if you started it static. Everything would attract everything else, and it would all collapse to a singularity. So Einstein was still convinced that the universe was static, however. So he realized that he could add to his equations, the equations that describe how gravitational fields are created. He could add to those equations a new term, which he called the cosmological term. And the number, the coefficient in front of that term is what we call the cosmological constant. And this term created gravitational repulsion. And it allowed him to build a static model of the universe by adjusting this term to have just the right value to hold the universe up against the normal attractive components of gravity. Modern particle physics suggests that at super high energies, there should be many states which have the same property as Einstein's cosmological term and would create gravitational repulsion. And inflation supposes that at least a speck of this repulsive gravity material existed in the early universe, and that speck would become the seed for our Big Bang. So the sequence of events goes as follows. Inflation proposes that at least a patch of this repulsive gravity material existed in the early universe. And here I have to admit that we don't know exactly when inflation happened. Inflation is a very successful theory, as I'll be telling you, but nonetheless, the successes don't depend on exactly when it happened. And that means we don't know exactly what the energy density of the universe was when inflation happened. So the numbers that I will give you will be sample numbers based on the assumption that inflation happened at the energy scale of what are called grand unified theories. But there's pretty much uncertainty about these numbers, except whatever numbers I gave you, they would seem off scale compared to anything in our experience. If inflation happened at the scale of these grand unified theories, then this initial patch, which will become the seed for our entire observable universe, needs to only be as large as 10 to the minus 28 centimeters when all this starts. Now, I assume most of you know what that means, but in case you don't, I thought I'd write it out. It's that. Now, since the patch is going to be enlarged fantastically by inflation, the initial density of such patches, or even the probability that they exist, can initially be very small, as long as there's at least enough probability so you expect that one of these should exist in the early universe. The gravitational repulsion would then take over if you had this patch, and it would drive that patch into exponential expansion. And that means that this patch will double in size, and it will double in an incredibly short length of time, about 10 to the minus 38 seconds. And then if you wait 10 to the minus 38 seconds again, it will redouble and redouble and redouble. And that's what is meant by the word exponential expansion. And it's amazing how fast numbers grow when you keep doubling and doubling and redoubling. So to get from the patch of 10 to the minus 28 centimeters, I didn't mention it, but this is more than 1 billion times smaller than the size of a single proton. So it really is tiny. To get from this size to what we need to build our universe requires only about 100 doublings. At the end of the 100 doublings, it's not as big as our universe. It's, in fact, only about 1 centimeter across, about the size of a marble, I say here. Marbles are 1 centimeter across, of course. But that's still big enough so that the continued coasting that happens from that time onward allows this tiny region to become large enough today to encompass literally everything that we can see, our entire observable universe. The full universe might be much larger than that. We have no idea how big the full universe is, but we do know what the observable universe is. So we could have had, by the way, many more than 100 doublings, and that would be perfectly okay. There's nothing here that needs to be fine-tuned, but we do need at least 100 doublings in order for this tiny patch to be able to explain the entire observed universe today. Define 10 to the 28, in case. Okay, going on. The repulsive gravity material is unstable, which is what allows inflation to end. So the repulsive gravity material ultimately decays, much like a radioactive substance decays, ending inflation. And when that decay takes place, the energy that had been locked up in this repulsive gravity material, now I'm just talking about its rest mass energy, gets converted into all kinds of other particles, which then form a hot soup of particles, which is exactly the initial conditions needed for the conventional Big Bang theory. So the idea is that inflation sets up the initial conditions for the conventional Big Bang theory, and essentially all of the particles that we now see in the universe are created during the decay of this repulsive gravity material. Now, a very important feature here, which is kind of strange, we're undergoing a fantastic amount of expansion here, 10 to the 28 linearly, and the volume goes like the cube of that, so the volume is increasing by 10 to the 84, fantastic factor. If this were like a normal material that thinned out when the volume expanded, there'd really be nothing left by the end of inflation. You'd just have an empty universe. But a very important feature is that this peculiar repulsive gravity material actually does not thin out as it expands. It actually maintains a constant density as it expands, which sounds like it must violate conservation of energy. We seem to be getting more and more energy in the mass of this ever-enlarging region, which has a constant density of mass. So there has to be some way for us to get out of this. And clearly, this is the point where I mentioned there was going to be 2 miracles. Here's where the second one comes in. The second miracle is that although energy is unambiguously conserved, we're not going to make any changes about that statement. It turns out, though, that energies are not always positive. And that really changes the whole picture. If energies were always positive and they were conserved, the only way to ever get a lot of energy would be to start out with it. But if energies can be positive or negative, then there's another option. And in fact, the energy of a gravitational field is unambiguously negative. And that's a statement which is actually true both in Newtonian gravity and in general relativity. So what that means is that the negative energy of gravity has the possibility of canceling out the positive energy of all the matter that's being created so that energy can be conserved. And that's exactly the way it works. As inflation is going on, more and more positive energy is appearing in the form of the matter, the repulsive gravity material that's filling this region. But at the same time, more and more negative energy is appearing in the form of the gravitational field that fills the region. And everything is consistent with the total energy remaining conserved, which means it remains incredibly tiny and could be exactly zero. There could be, for all we know, a perfect cancellation between the positive energy of matter in the universe and the negative energy of the gravitational field that fills the universe. So an accounting sheet would look something like this. The total energy of the universe will consist of a huge, can't tell it's huge, but that's huge, a huge amount of energy positive, shown in the black, consisting of matter and radiation, but there's also a huge negative contribution, shown in red, of the gravitational field that fills the universe. And the total energy of the universe is completely consistent with being zero. There's no energy needed to produce the universe that we observe, and that's why inflation could do it, starting from essentially nothing. Okay, that completes the first part of my talk, the part where I tried to explain how inflation works. So now I'd like to change gears a bit and try to convince you that this is not just a nice story that one can tell, but in fact, there's significant evidence that our universe, the universe that we observe, actually began in this way. And I want to talk about three pieces of evidence, the first of which is the large-scale uniformity of the universe. The fact that the universe looks the same no matter what direction we look, as long as we average over big chunks of volume. And this uniformity is seen most emphatically in the cosmic background radiation, the radiation that we view as being the afterglow of the heat of the Big Bang itself. And this radiation has now been measured very carefully by astronomers, and it's known to have the same intensity in whatever direction you look in the sky, to an accuracy of 1 part in 100,000, which really is unbelievably uniform. Now, to understand what that means about the early universe, I should tell you a little bit about what we think about the history of this radiation. A crucial point is that before about 380,000 years, the universe was so hot that the matter would have been in the form of a plasma, free electrons and free nuclei wandering around through space. And it turns out that a plasma like that is very opaque, very non-transparent to photons. And it's really the free electrons that do it. The free electrons have a very large interaction rate with photons. So the photons are constantly being scattered off of the electrons. So during this early period, before 380,000 years, the photons that now make up the cosmic background radiation were all there, by and large. And they were moving at the speed of light, because light always moves at the speed of light. But each individual photon was constantly changing directions as it collided with an electron and scattered. And therefore, even though instantaneously each photon was moving at the speed of light, the photons really didn't get anywhere during the first 380,000 years, simply because of this rapid change in direction. So for the first 380,000 years, the photons can be thought of as being frozen with the matter. They just followed the matter. But at 380,000 years, according to our calculations, the universe finally cooled enough so that the matter neutralized and became a neutral gas, like the air in this room. And like the air in this room, the neutral gas that filled the universe was highly transparent. And that meant that the photons that we observe today in the cosmic background radiation have really just been traveling on straight lines since 380,000 years after the Big Bang. And that in turn means that when we look at the cosmic background radiation, we're effectively seeing an image, a snapshot of what the universe looked like at 380,000 years, just as the photons traveling from my face to your eyes give you an image of what I look like. So the bottom line here is that the uniformity that we see in the cosmic background radiation can be translated into an implication of uniformity of the universe at 380,000 years. The matter density of the universe, we know from these observations, must have been uniform to 1 part in 100,000 at 380,000 years after the beginning. So the question is, can we explain that? Can we understand how the universe got to be so uniform? Now, we do know that things tend to become uniform. The air in this room tends to scatter out to fill the room. The air in this room also tends to come to a uniform temperature. And both of those effects are sometimes called the zeroth law of thermodynamics, the approach to thermal equilibrium. So you can ask yourselves, can we explain the uniformity of the early universe by those kind of processes? The answer in the context of the conventional Big Bang theory is a resounding no. And the way that one understands that the answer is no is simply by looking at the time involved and the distances that are involved. And it turns out that for the universe to smooth itself out by 380,000 years, if it didn't start out smooth for some unknown reason, but if it didn't start out smooth, for it to smooth itself out by 380,000 years would require matter and energy to move around at about 100 times the speed of light. And within the laws of physics as we know them, nothing travels faster than light, ever. So there's no way, within the context of the conventional Big Bang theory, that this uniformity can be explained. Now, I should add that you can always assume the uniformity. We don't really know how the universe was actually created. So if you wanted to just assume that it started out perfectly uniform, that's enough to explain why it looks uniform. But that's just an assumption. It's not an explanation of anything. If one wants to have an explanation in the context of the conventional Big Bang theory, it just can't be done. But inflation gets around that. In inflationary models, the key issue is that inflation inserts into the history of the universe this period of dramatically large exponential expansion. And what that means is that if we take the observed universe today and imagine following it backwards in time, when we come to the period of inflation, where the universe was rapidly expanding, following it backwards in time, it rapidly contracts. And before inflation, the region that's going to become our observed universe was vastly smaller in the inflationary model than it would have been in the conventional Big Bang theory. That opens a new door. While the universe was so incredibly small before inflation, there was, in fact, plenty of time for it to become uniform by exactly the same kind of processes that allow the air in this room to spread itself out uniformly and come to a uniform temperature. And then, once the uniformity is established on this very tiny scale, then inflation could take this tiny region and stretch it out to become large enough to include everything that we now see. So inflation gives a very natural explanation for why the universe should look homogeneous, while in the conventional Big Bang theory, it actually seems very mysterious how the universe could ever have become so homogeneous. Okay, next item that I want to talk about is something called the flatness problem. Basically the question of why was the early universe so flat? First question you might want to ask is, what do I mean by flat? What I mean has to do with the geometry of space. According to general relativity, space is not necessarily Euclidean, General relativity allows three-dimensional space that we live in to be curved. It's hard to visualize that, but it's distinctly what general relativity allows. The kind of curvature that one speaks about in cosmology has analogs in 2 dimensions, which are much easier to visualize. So these pictures here show the kinds of geometry that are alternatives to flat geometries. They're shown in 2 dimensions, but it's only an analogy. We're really talking about 3 dimensions. So one possible geometry is called a closed geometry. And one way of describing it is in terms of what happens to triangles. We all learned in high school from Euclidean geometry that the sum of the 3 angles that make up the corners of a triangle always add up to 180 degrees. If you draw a triangle on the surface of a sphere, you can see that that's not true anymore. The sum of the 3 angles is always greater than 180 degrees. And that also carries over to the 3-dimensional geometry that we're describing as an analogy to this surface of a sphere. Conversely, there's an open geometry which resembles a saddle kind of a shape in a 2-dimensional analog. And on the saddle, if you draw a triangle, you could see that the edges get pinched, and the sum of the 3 angles will be less than 180 degrees. And then there's, right between these two, there's the flat geometry, which is the geometry of Euclid, the geometry in which every triangle has exactly 180 degrees. According to general relativity, the flatness of the universe is related to its mass density. And astronomers define a number called capital omega, capital Greek letter omega, which is just defined to be the actual mass density of the universe divided by something called the critical mass density, where the critical mass density is exactly that density that gives the flat geometry. It's not a universal constant, by the way. The critical mass density depends on the expansion rate. But for any given expansion rate, there's a value that you can calculate for the mass density that would make the universe geometrically flat, that is, obey Euclidean geometry. So that means that if omega is 1, that is the flat Euclidean geometry. If omega is bigger than 1, that gives you this closed geometry. And if omega is less than 1, that gives us an open geometry. Now, a key fact about this quantity omega is that the way it behaves as the universe evolves is very much like a pencil balancing on its tip. It's an unstable equilibrium, where the unstable equilibrium point is omega equals 1. So that means that if omega is exactly equal to 1 in the early universe, it will stay exactly equal to 1 forever, just as a pencil that's perfectly balanced on its tip will stay up forever, at least according to classical physics. Never mind quantum fluctuations. We'll ignore those for now. But if the pencil is leaning just the tiniest bit in any direction, it will rapidly fall in that direction. And that is the same as omega. If omega in the early universe is just slightly greater than 1, I'm sorry, I'm supposed to start here. If omega in the early universe is just slightly below 1, it rapidly falls to 0. And the universe just thins out, and there's no time for galaxies to form. If omega in the early universe was just slightly greater than 1, then the universe, then omega would rapidly rise towards infinity. And omega being infinity just means the universe has reached its maximum size, and then it collapses. So if omega in the early universe were just slightly bigger than 1, the universe would have rapidly recollapsed. And again, no galaxies would have formed. And to be quantitative about this, to be as close to the critical density as we measure today, if we trace it back to 1 second after the Big Bang, and that, by the way, I might remind you, I think I mentioned, is the beginning of the processes of Big Bang nucleosynthesis. So I think we really have evidence that our theory works at 1 second. If we trace back to 1 second, omega at that time must have been equal to 1 to 15 decimal places. So I sometimes joke and say that the best known number in physics is the mass density of the universe at 1 second after the Big Bang, because we know it to 15 decimal places, which really is incredible. And the reason we know it so accurately is simply that the evolution of the universe has amplified any deviation from omega equals 1. The key point is that in conventional cosmology, we need omega to be 1 to incredible accuracy for the Big Bang theory to work, to explain the universe that we see. But there's nothing in the conventional Big Bang theory that causes omega to be 1. The theory would have been equally logically consistent if omega started out being a half or 10 or anything really. But it would only describe our universe if omega starts out being 1 to 15 decimal places. So inflation solves that problem. That is, explains why omega is equal to 1. Because it turns out that during inflation, everything is different. Because gravity is behaving repulsively, the equations of how omega evolves also change. So during inflation, instead of omega being driven away from 1, which is how the behavior works at every other time in the history of the universe, during inflation, omega is actually driven towards 1, and it's driven towards 1 powerfully, quickly. If we have the amount of inflation that I talked about, 100 doublings, that's enough to allow omega to start out generously far from 1 and still end up being close enough to 1 at the end to explain our universe. And in fact, omega in an inflationary model really could begin at any value you choose. The further away you start it from 1, you need a little bit more inflation to drive it to 1 by the end of inflation. But inflation is very effective at driving omega to 1. So one never needs much more inflation than the 100 doublings that I mentioned to explain why omega is so extraordinarily close to 1 by the end of inflation. Now, since this mechanism of driving omega to 1 is so efficient, inflation really predicts that today omega should still be 1. It should be driven so close to 1 that even though it starts to, in principle, deviate from 1 after inflation, it should still be, the pencil should still be balanced perfectly on its tip. And the only way to avoid that is to have inflation end at just the right time, which seems highly unlikely. So we have a prediction that omega should be 1. Now, until 1998, observation was pointing towards a much lower value of omega, a value of omega of 0.2 or 0.3. And this was a problem for inflation during that period. And I have to say, personally, it meant for me that it was very uncomfortable for me to have dinner with astronomers. Astronomers would like to look at me and sneer a little bit and tell me that they're aware that inflation is a very beautiful theory and it sounds very nice and all, but it can't be right because inflation predicts that omega should be 1, and it's not 1. They were confident that omega was 0.2 or 0.3. So all this changed, however, in 1998. And in fact, the latest observation of omega, and this is an observational number, not a theoretical number, is 1.0010 plus or minus 0.0065. The fact that this number is so close to 1 seems to be a little bit lucky given that error. But it does mean that we do know that to about 0.5%, that omega is equal to 1, exactly like inflation predicts. And the difference between the pre-1998 and the post-1998 numbers is the new ingredient, which is dark energy. The key event that happened in 1998 that I'm referring to here is that in 1998, it was discovered that the expansion of the universe was not slowing down under the influence of gravity, which is what most of us expected, including me, but rather has been accelerating for about the last 5 billion years. And that means that the universe today is actually filled with some kind of repulsive gravity material. And we call this repulsive gravity material that fills the universe today the dark energy. And even though we're not absolutely sure about what this dark energy is, we can still calculate how much of it there must be in order to create the gravitational repulsion that we see. And it's when that is added in to the rest that the 0.2 or 0.3 comes up to 1. So the bottom line really is that the astronomers that I was having dinner with were actually right about the matter that they were looking at. It did not add up to omega equals 1. But there was a whole component that neither they nor I knew at the time existed, which brought omega up to 1, perfectly consistent with the inflationary prediction. Okay, let me move on to the third item that I want to discuss as evidence that our universe really underwent this process called inflation. I want to talk about the small-scale non-uniformities. On the larger scale, the universe looks incredibly homogeneous, but there are, of course, inhomogeneities. We wouldn't have Switzerland if there weren't inhomogeneities, for example, and lots of other things. And we can, in fact, see these inhomogeneities even in the cosmic background radiation itself. I told you that astronomers have carefully measured the cosmic background radiation and discovered that it's uniform to 1 part in 100,000. What is even more amazing is that they have measured the non-uniformities at the level of 1 part in 100,000. So the picture of the cosmic background radiation, which is also a picture of the matter distribution in the early universe, is that it was almost completely uniform, but there are tiny ripples on top of that background of almost complete uniformity. And those ripples are now a subject which have been studied very, very carefully. We now know a lot about those tiny ripples in the cosmic background radiation. So the question is, where do these ripples come from? In conventional Big Bang cosmology, there really was no explanation for the ripples. There was really no explanation for the uniformity either. So naturally, there's no explanation for the limitations on that uniformity. But in inflation, we have a theory which is much more predictive. At the classical level, the enormous expansion of inflation just stretches everything out and causes it to become uniform. And in the early days of inflation, there was a period of about a year or so when those of us working on inflation were very worried that inflation would die because inflation would lead to a completely uniform universe, and then there would be no possibility of galaxies forming. These ripples had not yet been seen at that time, but everybody knew that they had to be there because they're really needed to explain how galaxies form. Then it was realized that quantum theory can come to our rescue. It's a little bizarre to imagine astronomical entities like galaxies and clusters of galaxies being created by quantum fluctuations, but that is the theory. The key point here is that classical theory is completely predictive, and if we treated inflation as a classical phenomenon, and by classical I just mean non-quantum, if we treated inflation as ignoring quantum theory, everything would just be smooth, and we would be predicting that the mass density would be exactly the same everywhere. But quantum theory is a fundamentally probabilistic theory. It's not completely predictive. So where the classical approximation would predict a completely uniform density, the quantum theory would predict that in some places the actual mass density would be a little bit higher than that predicted average. In other places, the mass density would be a little bit lower than that predicted average, just by the chance probabilistic behavior of quantum theory. And that gives you a pattern of ripples on top of the uniform background, which is exactly what we're looking for. And one really can apply the mathematics and figure out what inflation predicts in the context of a quantum mechanical description of inflation. It turns out that we don't know enough about the details of this repulsive gravity state that I've told you about to be able to really calculate the height of these ripples, the amplitude of the ripples. But what we can calculate is something called the spectrum of the ripples. And by spectrum, I mean pretty much the same thing that you would mean if you talked about the spectrum of a sound wave, which is a much more common notion. When you talk about the spectrum of a sound wave, what you're imagining doing is breaking up some complicated sound wave into components, each of which have a definite wavelength. And then the spectrum is simply a description of how the intensity varies with the wavelength. How much of each wavelength do you need to build up the complicated description that you started with? And one can do the same thing with the pattern of the cosmic background radiation on the sky. We can break up this pattern of hot spots and cold spots, small variations of the effective intensity or effective temperature. We can break up that pattern into components of definite angular size, and then talk about how the intensity varies with the angle. And inflation makes a prediction for what that should look like, and the astronomers can measure what that looks like, which is even more fantastic. And even more fantastic still, they agree. To summarize, and then I'll show you the graphs in a second, but inflation attributes these ripples to quantum fluctuations, and inflation makes generic predictions for the spectrum of these ripples, that is, how the intensity varies with wavelength. When I use the word generic here, by the way, what I mean is that, in fact, inflation is not really a detailed theory because of the fact that we don't really have a detailed theory for the structure of this repulsive gravity material. So inflation is really kind of a class of theories with different possible descriptions for the repulsive gravity material. And when I say there's a generic prediction for the spectrum of the ripples, what I mean is that the detailed prediction depends on the details of the model, that we don't know what the right model is. But there's nonetheless a prediction that most of the models make, and we can test that. And that's what I'm comparing here. So I'm really showing you what the simplest class of inflationary models predict. And it turns out that they agree incredibly well with the actual data. So here is just a picture of what the sky looks like. This is the microwave sky as seen by the Planck satellite, which is the most recent satellite that's been used to measure the fluctuations of the cosmic background radiation. These different colors represent different temperatures. It's a very small band. It's a false color, of course. If you actually looked at it, it would just look completely smooth. These variations are only at the level of 1 part in 100,000. And you can see the scale here. It's in micro Kelvin. So these are incredibly small fluctuations, but they can still be seen unbelievably clearly with the wonderful data that these satellites have been bringing back. Now, the next graph I'll show you is the spectrum. This is the spectrum from that same data from the Planck satellite. What's being plotted is the intensity of the fluctuations, temperature fluctuations in microkelvin squared, as a function of the angular scale, where the largest angles are at the left and the smallest angles are at the right. And if you know about multipoles, the analysis is really done in terms of multipoles, dipole, octopole, et cetera. But these numbers really tell the story well enough. And the data, the dots represent the data. Some of the dots you can see error bars. The vertical bars with the cross bars on top and bottom are the errors of the measurement. Some of the measurements are so precise that you can't see any error bars. The measurements become more precise on the right for what really is an obvious reason. If you're talking about a very small angular scale, like 0.1 degrees, you have many, many samples of size 0.1 degrees on the sky. But if you're talking about an angular size of 90 degrees, you have very few samples on the sky. And that's why you can get much more precision on the right of this graph than you have on the left. So the error bars get big on the left. The green line is the predictions of inflationary models, or the simplest inflationary models. And as you can see, it's just a beautiful fit. Now, I should admit that this fit is based on fitting 6 parameters to the data. But of those 6 parameters, there are really 4 of them that we already knew pretty well, and we're only fine-tuning by fitting them to this data. So there are really only 2 parameters here that are really being fit cold. One of those is the overall height of the graph. As I mentioned, we can't really predict the overall intensity of these ripples. Whoops. And another parameter that's being fit purely to the data, because we don't have any other way of estimating it, is the data depends on how much absorption there is between the cosmic microwave background radiation and today. And there's a free parameter in the fit for that number. And that changes the overall shape of the curve a little bit. But by and large, it's still an incredibly good fit, and I think everybody agrees it is. I thought I'd give you a quote here from a report of a committee to know what committees think about this. So this is the Dark Energy and CMB Working Group of the American Physical Society, which wrote a report in 2013. It's a 94-member group. And they said that current measurements of the cosmic microwave background and observations of large-scale distributions of dark matter and galaxies in the universe are in stunning agreement with the concept of inflation. So the data they're talking about is the data I just showed you plus more. And it all fits incredibly well with what inflation predicts. OK, I want to mention one other aspect of data because it's been talked about in the press significantly, and that is the issue of gravitational waves coming from the early universe. Inflationary models predict that there should be gravitational waves in the early universe generated by pretty much the same quantum processes that generate the density non-uniformities that I just showed you graphs of. The evidence for gravitational waves came and went over the past year or so. It began very dramatically on March 17th, 2014, when a group called BICEP2, centered at Harvard, but involving also 4 or 5 other universities, announced in a well-publicized press conference the detection of patterns which are called B-modes in the polarization of the cosmic microwave background. And these particular patterns can, in principle, only be created by gravitational waves in the early universe. So they announced that they had seen gravitational waves exactly like inflation predicts, and it was considered a huge success for inflation. And I was called up by newspapers every hour. It was an incredible publicity event. The result that they announced was that if they accounted for their best estimate for the contamination due to dust, they found a tensor to scalar ratio. That means a gravitational wave perturbation to the density perturbations that I showed you, with a ratio R of 0.16 with some error bars. And they said R equals 0, which would mean the absence of gravitational waves, disfavored at 5.9 sigma. That language is a little technical, but I'll translate. The translation is that they were claiming that the probability, given their data, that there were not any gravitational waves from the early universe was only at the level of about 1 part in a billion. The results look golden, as they were originally announced. But unfortunately, over the next months and year, ultimately, more and more analyses were done by other people, concluding that there was a significant amount of dust in our galaxy. And it turns out that dust can also produce these B-modes. And the bottom line is that as far as we know today, the entire signal could have been dust. There might have been real gravitational waves from the early universe. We can't exclude that possibility. But the signal seen is completely consistent with having nothing but dust. So the bottom line, I think, was announced in a joint analysis by the BICEP2 group in collaboration with the Planck satellite people. And they said that we find strong evidence for dust and no statistically significant evidence for tensor modes. So the tensor modes have gone away. Now, we still might find them. The search for tensor modes is still very much on, search for these B modes. And if they are found, it really would be a very important thing. It would not only provide yet one more strong piece of evidence for inflation, but these B modes would allow us to determine something about inflation which so far we have no other way of determining, which is the time at which inflation occurred, or equivalently, the energy density in the universe at the time inflation occurred. That energy density of the universe at the time of inflation strongly affects these B modes and doesn't affect anything else that we have any way of seeing at the present time. So it would be a tremendous tool for studying inflation if we can find these B modes. And people are looking. The current limit on this quantity R, which is the measure of the strength of B modes, we haven't seen them, but R is being pushed down. It was 0.11 prior to BICEP2, and BICEP2 thought they saw it to 0.16. Now the limit is down to 0.07, and and this limit was just announced about a week ago, which indicates how quickly these results are coming out. In the future, the people who are designing these future experiments tell us that if far as even as small as 0.001, a factor of 100 smaller than what we're now looking at, they can find it by about 2024 by a set of experiments that go by the generic name of CMB stage 4. So within about a decade, we'll be pushing our sensitivity to these B modes by a factor of 100 beyond where we are now. And if we see them, it will be incredibly exciting. I do want to mention, however, if we don't see them, that is still actually not evidence against inflation, because there's a wide range of inflationary models, as I mentioned earlier. And there are models which give predictions for the B mode intensity that's significantly smaller than 0.001. So not seeing B modes will never be evidence against inflation. But if we do see them, it's another very strong piece of evidence in favor of inflation. OK, this concludes what I wanted to say about evidence for inflation. And let me summarize the key 3 main points where that inflation can explain the uniformity of the universe. Inflation can explain why the universe is so incredibly close to being flat. And finally, inflation can give us an incredibly good picture of the density fluctuations that we see in the cosmic background radiation, the pattern of ripples in the cosmic background radiation that astronomers observe. And B modes might become evidence for inflation in the future, but they're not now. OK, moving on, I wanted to conclude the talk by telling you what inflation says about the possibility of a multiverse. And as I mentioned in my introduction, inflation does make the multiverse look very plausible. And the key idea is that almost all detailed versions of inflation lead to what we call eternal inflation, and hence a multiverse. And by eternal inflation, what I mean is, in these models, once inflation starts, it never completely stops. It goes on inflating, in some places at least, forever. And the way that happens is really pretty simple to see. I mentioned to you that inflation is driven by this repulsive gravity material, and that the repulsive gravity material is unstable. But it really is unstable in a way that's very similar to radioactive substances. And as you probably know, if you have a radioactive substance, one atom, for example, of some unstable isotope of uranium, you cannot predict when it will decay. You only know that there's a certain half-life. And if you wait for a half-life, there's a probability of a half that it will decay. But you have no way of predicting whether it will or not. It's just a 50-50 quantum mechanical choice, which is unpredictable. And it's similar for the inflating material. You can also, if you want, describe it by a half-life. And if you wait for a half-life of this repulsive gravity material, then really by definition, half of it will no longer be inflating. It will have converted into normal matter, which is not gravitationally repulsive. But the thing is that while this repulsive gravity material is waiting to decay, it's continuing to exponentially expand. So if you wait for one half-life, indeed, half of it will have decayed and will no longer be inflating. But the half that's still inflating will, because of the exponential expansion, be vastly larger than what you started with. So you're not really making any progress at all towards ending inflation. The prediction for these models is that the inflation will go on forever, where the inflating region gets bigger and bigger, and within this inflating region, pieces go normal, decay, and when the decay takes place, a local universe is formed at that location. A Big Bang is created, essentially, and we call those pocket universes, just to distinguish from the use of the word universe, as sometimes people talk about universe as everything that exists. And that's not what we're talking about here. So here, when we talk about a universe, we're talking about a Big Bang and a large space-time that evolves from it, just like what we see. So we would be living in one of these pocket universes. And the system would go on producing pocket universes forever. Literally an infinite number of them in the context of our mathematical models. Now, when I first was told about this by various friends, I said, yeah, it sounds true, but why should we care? We're never going to be able to see these other universes anyway, and how does it help us understand our universe, which is what the goal of cosmology really is. Some of my friends were just very excited about the idea that there could be other universes, which that's okay. People are allowed to be excited about whatever they want to be excited. But what I want to emphasize now, though, is that since 1998, there really is an important issue relevant to our understanding our own universe, which might depend on this issue of a multiverse. So what I want to talk about is what really is now viewed by many as the most, the deepest problem in fundamental physics today. And that is the problem of what's called the cosmological constant problem. And it's related to this discovery of dark energy in 1998. In 1998, as I mentioned, astronomers, and in particular there were two groups of astronomers, discovered that the universe was not slowing down, but in fact was accelerating in its expansion, and apparently has been accelerated in its expansion for the past 5 or 6 billion years. And according to general relativity, this requires some kind of repulsive gravity material, which was dubbed dark energy. But there is a simple explanation for what this dark energy probably is, and all observations so far are consistent with this simple explanation. And I'm going to go on the assumption that this simple explanation is correct, namely that the dark energy is simply vacuum energy, the energy of empty space. Now, you might wonder how empty space can have an energy density. If it's empty, what's there to have energy? And that's no doubt what Einstein himself thought. But Einstein was really living in an era of classical physics and was thinking classically about empty space. But modern physicists don't think about empty space that way. Empty space is now not at all empty from the point of view of a modern quantum description of what space is like. In particular, in empty space, there are, for example, electric and magnetic fields. And you might think that in empty space, those would just be zero. But in fact, there are quantum mechanical uncertainty principles which say that they can't be zero and stay zero. If they're non-zero at any instant, they grow instantly. It's something huge. So the electric and magnetic fields are required by quantum theory to have non-zero fluctuations in the vacuum. And that involves energy. Huge amount of energy. And it isn't just the electric and magnetic fields. Modern particle physicists assign a field to every elementary particle. So there's also, for example, an electron field in modern particle physics. And the electron field also fluctuates and carries energy. It turns out, in fact, that the electron field carries negative energy. So it is important here and interesting that there are both positive and negative contributions to this vacuum energy. In addition, in the modern picture of the vacuum, there's at least one field, the field that we call the Higgs field, the field connected with the particle discovered at CERN 2 years ago. This Higgs field is believed to have a non-zero value everywhere in space. And that, of course, also has energy associated with it. So it's easy for particle physicists to believe that the energy of the vacuum is non-zero. We don't really know how to calculate it, by the way, because we don't know what all the contributions actually are. But we can nonetheless estimate what we expect the vacuum energy to look like based on knowing some of the contributions. And the key problem, what particle physicists don't understand, is what makes the value of the energy density what it is. The observed value is, in fact, vastly smaller than what particle physicists would estimate the energy density of the vacuum ought to be based on the contributions that we know exist to it. So even though we cannot calculate the vacuum energy density, there's a natural particle physics estimate of it, which is what's called the Planck scale. It's actually the energy scale at which the effects of quantum gravity are believed to become important. And this Planck scale is much larger than the observed energy density. It's in fact larger by 120 orders of magnitude. Fantastic disagreement between what we observe and what we would naively expect. So this becomes a very deep problem for people concerned with fundamental physics. What in the world is it that causes the energy density of the vacuum we are living in to be so unbelievably small compared to what we might expect? And the reason this is relevant to the multiverse is that there is a possible explanation here which comes out of thinking about the multiverse. So I try to explain that on this slide. The first item here is just a reminder of what I've already told you, that one of the thorniest problems in particle theory is to understand why the energy density of the vacuum is so incredibly small. The multiverse offers a possible answer, although I do say right here that it is a controversial answer, which it is. I don't want to advertise this as something that physicists agree on. We don't, and I'm not going to even advertise it as being necessarily true in my own opinion, but I think it is a solution which we need to take seriously as a possible solution. A key ingredient of this argument is a fact that comes out of string theory. String theory appears to be our best attempt at a quantum theory of gravity. We don't yet have any experimental verification of string theory, but as the most clearly consistent quantum theory of gravity that we know of, I think it still is something we should take seriously. And according to string theory, there's not just one kind of vacuum, but in fact, there's a huge number of types of vacuum. String theorists talk about numbers like 10 to the 500 different types of vacuum that can exist in string theory. And by vacuum, what we really mean here is a very long-lived, usually metastable state, but a state which is stable enough to actually explain the vacuum of our universe, because its decay rate is so unbelievably small. And each of these types of vacuum would have their own vacuum energy densities. They would have their own structure internally, which would lead to different vacuum energies. And they would span a full range from something on the order of the Planck scale at the high end to negative the Planck scale at the other end. These vacuum energies can be positive or negative. And they'd be everywhere in between, and very dense, because there's 10 to the 500 of them spread, over this region. No, wrong way. I'll get there. There I am. So with 10 to the 500 different choices, the expectation would be that there would be, in fact, a huge number of vacua whose energy densities would be as small as what we observe, although these very small energy vacua would still be an incredibly small fraction of the total. So string theory gives us at least the possibility of producing vacua like the one we observe. But there's still the question of why should we expect to find ourselves in such an unusual vacuum, even if many of them exist. If there are many more that are very different, why aren't we more likely living in the many more? So there's an answer to that, and this is where things become a little bit controversial, unless we don't know how much to trust this answer. But the vacuum energy certainly affects the ability of life to evolve. It affects the acceleration of the universe. So if the vacuum energy were of the order of the Planck scale, the universe would fly apart in a tiny fraction of a second, and it's clear that no life could form. And similarly, if the vacuum energy were negative and of the magnitude of the order of the Planck scale, the universe would just implode in a tiny fraction of a second, and clearly no life would form. So there's an argument that says that life will only form in a fairly narrow range of vacuum energies near zero. And if that's true, that could explain why we see such a small vacuum energy. The general picture would be that in most of space, the vacuum energy would still be huge, as our intuition suggests, but that most living things in this multiverse would see an incredibly small vacuum energy. And that is believed to be sufficient to explain why we, as living things, see a very small vacuum energy. So as I said, the explanation is controversial, but it certainly is nonetheless taken seriously and is discussed at almost any cosmology conference. I'd like to, in fact, close by giving you a bit of a survey of how seriously physicists take this idea of a multiverse, by giving you just a few sample quotations of well-known physicists. So I want to start with Martin Rees, Astronomer Royal of Great Britain. I should get rid of this cursor, finally. He's Astronomer Royal of Great Britain and former president of the Royal Society, former master of Trinity College at Cambridge, has most every honor you could think of. He's been knighted as well. He is a fan of the multiverse. And at a conference a few years ago, someone was interviewing physicists about this question. He said that he's sufficiently confident about the multiverse to bet his dog's life on it. Now, I have to admit, I've never met Martin Rees's dog, so I'm not sure exactly how high those stakes are, but I assume it's a very cute dog, and that's a pretty significant statement. Now, at the same conference, Andre Linde from Stanford, a person who I shared the 2014 Kavli Prize with, a person who played a key role in the development of inflationary models, who is a big fan of eternal inflation, he said that he has enough confidence to bet his own life on it, which is clearly really high stakes. Now, the person who I always regard as the voice of reason in many things is Steven Weinberg, who you may have heard of, won the Nobel Prize in 1979 for the development of the electroweak theory, the theory of unifies the weak and electromagnetic interactions, and the first successful theory of the weak interactions. He was not at this conference, but he heard about it later and wrote about it. And in his writings, he said that he has just enough confidence about the multiverse to bet, think of something clever. He said there's just enough confidence to bet the lives of both Andre Linde and Martin Rees's dog. And I'll stop there. Thank you.
So thank you very much for these wonderful stories about miracles and how they're solved. It reminds me, your talk, the content reminds me of what Einstein used to say about his work at the patent office, at least in the beginning. He said, it gives much food for thought. So thank you very much. As always, we have time for questions or comments.
Phenomenology or multiverse? Phenomenology or multiverse?
Phenomenology of multiverse? Yeah, how will we ever know that we're living in a multiverse if it's true? There are, I guess I would say there are three possibilities, but how long they'll take or whether or not it's true at all, I can't say for sure. One possibility, which I think is a long shot, but people talk about it and study it, is that in this model of different pocket universes appearing in an eternally inflating universe, if two pocket universes happen to materialize close enough to each other, they will collide. And that leads to the possibility that our universe could conceivably have collided with another universe in its past. And if so, that would show up as a fairly distinctive pattern in the cosmic background radiation. And astronomers have actually looked for that. There really are papers about it. They have not found it. And it seems like a long shot, but in principle, one can imagine maybe it would happen someday. More realistically, I think, another way of possibly verifying the multiverse involves pinning down the details of the inflationary model that describes our universe. Right now, we know some things, but not a lot, about this repulsive gravity material that I talked about, which in particle physics language is described as a scalar field and its potential energy function. Measurements of the cosmic background radiation actually do strongly constrain how that scalar field behaves. And if it can be constrained enough so that it becomes convincing that the version of inflation that actually describes our universe is a version which leads to eternal inflation and a multiverse, then I think that could become very convincing. If the only way we could describe the universe that we see is to invoke a theory which says there should be many of them, I think we'd be pretty much forced to believe that there are many of them. And finally, the other kind of argument that leads to a multiverse and may ultimately become convincing is the controversial type argument that I described here. Right now, we can't understand why the vacuum energy density is so low. But if we believe in a multiverse, it becomes pretty much automatically explained. Those kind of arguments, from my point of view, are basically arguments of last resort. That is, you would not believe an argument like that unless you've tried hard to find another argument and have failed. But the more time that goes on and people fail to find other explanations, the more convincing the selection effect multiverse argument becomes. And there are other issues besides the cosmological constant that could also be invoked here. The vacuum energy, to me, is the cleanest by far of the different fine-tunings that we see in our universe that we can point to as things that we don't really understand. But there are a number of others as well. So one could believe that maybe sometime 50 years from now, people may become convinced on the basis of those arguments that the only way we can understand our universe is to imagine that it's part of a multiverse.
I think I don't go wrong in that you have convinced almost everybody here that this type of research or thinking is most exciting. And so that we are very glad.
Okay.
You leave it at that. But.
I had a feeling there was a but coming.
You tell me the
about
but first. Please do.
What?
No,
Oh,
my but is to still have to try to remain with some critical thinking and common sense. It cannot go on that way, that every 10 years we have dark matter, which is more dark in the simple sense than, okay? Things cannot be at the same time infinite and finite, and so on. So I would like to ask you a comment on whether you would extrapolate that the science of cosmology or the part of cosmology is not only exciting, but it is not lost yet.
Not lost yet. Well, I'm not sure if I know what to say, but let me go back and show you again my favorite graph in the whole world. We're getting there. That one. Skip it. There seems to be some delay in my computer here. Yeah, this is doesn't like to go fast. There. Okay. Now, I claim that an agreement like that cannot be ignored. There's something under there that's meaningful. So.
Look like uninterpretable.
What?
It's not to me.
What? It doesn't look.
It's perfectly all right. And it
Right.
must have a deeper interpretation, I think.
Well.
Two equals and things like that.
Well, there is, of course, an explanation for why this curve looks the way it does, which would take longer than this talk. But I'm not sure exactly if I understand your point. But I really do think that cosmology now is clearly not philosophy anymore. We really are getting real data, highly precise data, and we have the ability to compare that data with our theories. So I would say that cosmology is now very much in the mainstream of science, and that one certainly cannot dismiss it as being just vague ideas thought about by people who really should be called philosophers.
Okay, other questions or comments?
Yeah, as far as I know, there are several flavors of inflationary cosmology. Are there any data yet that favor or disfavor some of them?
The answer is yes. The data is getting better and better. It's a fairly technical plot that I didn't want to include in my talk, but what's been measured now to pretty good precision is a parameter called n sub s, which is a slight slant on this curve from left to right. A generic inflationary model produces a curve that looks very much like this, but if you can measure it really accurately, the extent to which the height, average height on the right compares with the average height on the left gives you a parameter that differs from one inflationary model to another called n sub s, the scalar index. And that has now been measured to 10% accuracy approximately. And we also have bounds on the amount of gravitational radiation coming from not seeing B modes. And it turns out that those two numbers can be put on a plot which shows which models are successful and which models don't work. And in particular, now I'll have to talk a little bit more technically than the rest of the talk. I mentioned that this repulsive gravity material is described usually by a scalar field by particle physicists. And the simplest kind of scalar field is one with just a parabolic potential energy function, a potential energy function proportional to the square of the field. That is now ruled out. Another simple model is where the potential energy function goes like the fourth power of the field. And that is just about ruled out also. We are getting data that is constraining the form of these theories in powerful ways. Although there's still essentially, in principle, an infinite number of theories that work. But there's an infinite number of theories that have been ruled out as well. And we are making progress narrowing down the range of parameters.
More? Now's your chance.
Although you may not believe in philosophers were thinking about multiverse from the Greeks. There is a lot of thinking about. So I, as a philosopher, do not hesitate to affirm the possibility of multiverse, of course. But another kind of question was always crucial. What is the ontological status of that? Because it's not the same as if you talk of the universe where we have excellent access in information, observation, and so on. And so the modality of speaking about multiverse, about other parts, are they really of necessity or the modality of possibility? What is not the same? There are many, even physicians, I read, speaking about virtual multiverse, but that's not the same status of universe as we know and live in.
Okay, well, I think that question has some relation to the question that was raised earlier. If there is a multiverse, how would we know? I certainly agree that at the present time, the ideas of a multiverse, I think, do fit in your language into the realm of possibility rather than the realm of anything that we've established the existence of. But I do think that this idea of a multiverse is real. As I mentioned, most versions of inflationary models lead to a multiverse. And if one wants to use those very inflationary models to explain what we see in our universe, and they do very well, then I think one is really forced to also accept the consequence that they are predicting the existence of other universes. And furthermore, you could just dismiss, perhaps, the existence of other universes as a question that we shouldn't really be interested in the first place. But with issues like the cosmological constant problem, it may very well be that the correct answer to why we see such a very low vacuum energy may indeed be because in the multiverse, life only forms in those universes where the vacuum energy is incredibly small. So I think the idea of a multiverse really can have important implications for understanding properties of our own universe. So my feeling is that it is part of science. We don't yet know for sure if it's right, but it is something we can study, and I would guess that in 50 years or so, it may take that long, there will be a general agreement about whether we are living in a multiverse or not. And I think there's at least a reasonable probability that the agreement will be that the answer is yes.
Well, I don't see any hands anymore. So, oh, there is, okay.
Well, in the universe, in theory, there's wormhole to connect galaxies. And is there a possibility that the tunnel connects pocket universes? Thank you.
Okay, so if I understood the question right, is do we expect there to maybe be wormholes that could connect one pocket universe to another? I guess I'd say that as far as I know, this week the answer is no, but it's a sufficiently difficult question, so next week the answer might turn out to be yes. The formation of wormholes is, at the classical level, is pretty well understood, and classically I think it would just not happen. But at the level of the quantum description of the underlying space, that's still very much up for grabs. So I think almost any wild idea that you might think of really has some chance of turning out to be true.
There's a question.
Yeah, I see.
Yeah, be brave, folks. I don't mind answering questions.
Thank you very much for such an interesting talk. I just had a question about if the multiverse was true, are there any predictions of what implications this would have for further science?
Right. Well, I think if we did become convinced that we live in a multiverse, it would, in fact, significantly change the way people concerned with fundamental questions in science proceed. Right now, we have what's called the standard model of particle physics, which has something like 23 free parameters in it. And we wonder what is it that determines those free parameters. And in cases where those parameters seem to need to be chosen very, very carefully, we worry about what's going on. And the general issue gets referred to by the word that particle physicists bandy around called naturalness. So one important example of naturalness is the question of the mass of this Higgs particle that was discovered at CERN 2 years ago. According to our theoretical description of the Higgs particle, for most sets of parameters, the Higgs would weigh vastly more than what we measured. And this doesn't even really depend on having the measurement from CERN. We already knew that from the way the Higgs interacts with other things and creates mass of other particles that the Higgs could not be as heavy as the value that would be expected. It would be expected really to have a value near the Planck scale for most parameters. The only way to get the Higgs mass to be as small as it is to very finely adjust the constants in the underlying theory to cancel things out. So people have wondered how that happens. And one of the key theories that have been invented by particle theorists to possibly explain why the Higgs mass is so light is what's called supersymmetry, which you may have heard of. Supersymmetry is a pretty symmetry, a very elegant symmetry in any case, and probably would have been invented in any case. But one of the key arguments in favor of supersymmetry really describing nature is that it could explain why the Higgs mass is as light as it is. Now, in fact, at CERN, experimenters have been looking for evidence of supersymmetry, and so far none have been found. So people are worried about that. But another possible explanation for why the Higgs mass is so light would be a selection effect argument. And that is probably the key alternative to some mechanism like supersymmetry. There might be alternatives to supersymmetry. So if we became convinced that there really is a multiverse and that the laws of physics that we see really are strongly affected by selection effects connected with the fact that we are living beings, then that would slant all of these arguments in favor of the selection effect approach, and looking for things like supersymmetry to explain why the Higgs mass is so low will become a less appealing endeavor. So I think it really is true that if we do decide that we're living in a multiverse, it will really change the kinds of questions that theoretical physicists ask. Let me give an analogy. An analogy that's often used for these selection effect arguments is the radius of the planetary orbits, which of course sounds very different from microscopic things like how particles interact and what masses they have. But the story about selection effects is really very similar. If you go back to the time of Kepler, you might remember that Kepler had this complicated model of icosahedra inside of dodecahedra, all of which was intended to be a way of calculating the relative size of orbits of planets. And the key issue is that to Kepler, the solar system was the universe. It was the work of God, probably. And things like the orbits of planets couldn't just be accidents. They had to be what they were because there was some fundamental principle, he thought, that determined what the orbits of planets should be. And he worked very hard trying to build such a theory. He was aware that he never succeeded because he was a good enough astronomer to measure things carefully enough to know that his icosahedron model didn't quite work. But still, the aim was to explain the orbits of planets from fundamental principles. And now we think, oh, that's nonsense. We know that there are many solar systems, not just one, and that they form more or less by complicated processes of gas clouds collecting. And planets have all different orbits in different solar systems, and that's okay. We know pretty well what the orbit of the sun has to be for us to be here. So there is an anthropic argument, a selection effect argument for our own planet, and we accept that. And we don't worry about the fact that it depends on these selection effects associated with life. So if we become convinced that our whole universe is really just a pocket universe in a multiverse of perhaps an infinite number of pocket universes, it will become very much like thinking of our pocket universe in the same way that we think of our solar system. And many of the properties of our universe then will be things that we will think of as just being accidents, like the radii of the orbits of different planets.
Okay, one more question? That's the last one, yes.
Okay, I have a question. Some time ago, Roger Penrose proposed to look for ring-shaped structures in the background radiation. Where is it now, this idea?
Yeah, well, that's a good question. I think where the idea stands is that Roger Penrose still believes that he's seen them, and he has a co-author who works with him, and they believe that they've seen these circles. Everybody connected with the study of the cosmic background radiation believes that they've not seen them. And various papers have been written explaining how the statistics of the actual probability distributions we expect are perfectly consistent with what we've seen, and that there's no evidence for circles on the sky. So I think the dominant community opinion is that there's no evidence to support what Roger Penrose is claiming, but he still claims it, and he's a smart guy, so you can decide what you want.
Okay, so let's be an end for today. Tomorrow at 5:15, come back and hear more. Thank you very much again.